Hey everybody, welcome back to Organic Chemistry. In this final video for the radical reaction, at least theory video, we're going to go over some different type of radical reactions. So we've done substitution. We understand all the steps related to substitution. And what we're going to find now is that it's very similar for these other type of reactions. So the first thing we're going to do is addition, but then we're going to learn about different types of substitutions, a little different than what we've seen so far. Okay? And that's pretty much going to wrap up this chapter. So, like I said, once you learn the foundation of substitution, it's pretty easy to add new things into it. So let's start here. Now, when we learned about alkenes back in the alkene chapter, I had taught you guys that when you use HBr in particular with an alkene, that when HBr is treated in peroxide, let's say H2O2, that the Br winds up on the lower degree. Right? So the Br is on the lower degree. And I had told you guys at the time that we're not going to learn the mechanism until later on, which is now. And that is because this is a radical process. So if it wasn't for the H2O2, right? So, or R2O2, if I had HBr by itself, then the Br goes to the higher degree, right? So we would expect to see this based on our mechanism on chapter, whatever, the alkene chapter, right? So you break the double bond, you make a carbocation, and then Br comes in. So this is what we would expect to see without peroxide. Now, this reaction that I'm going to show you is specific for just HBr. So you can't do this with HCl or HI. It only happens with HBr. So I'm going to actually move this over here so that we can focus in. So this is what happens with peroxide. Now again, I want to emphasize that this right here only HBr. Okay, so that's the only thing you can use here in order to make this work. Otherwise, it does the top. So if it was HCl in peroxide or HI in peroxide, it would just do what's up here. That's it. It would just do the traditional reaction. So this is very specific to just HBr. Okay? So the question is, how does this happen, right? What's the actual process that's going on? So this is the overall process, and it's a way of putting a Br on the lower degree of the two alkene carbons. Okay? Now, notice again, another thing to point out, that if I use Br2 and heat, then I would get a completely different thing. I would work on the alkane, right? So this is HBr. Just recognize that. It's not the same as Br2, and we'll talk about that next. Okay. So what would actually happen? Well, just like always, there's an initiation. And in the initiation, and by the way, let me also make this clear, you can have ROOR or H2O2. It doesn't matter. So these are peroxides. That's the key. So if this is H2O2 or R2O2, doesn't matter. R2O2 doesn't make a difference. Okay? So what's going to happen is, let's say we have ROOR and we have heat. We always need heat, right? That's required for any of these reactions to go. Well, the first thing that's going to happen during initiation is, as we expect, this is an initiator. Remember that? Back in the first theory video that I did with you guys in this chapter, we talked about different initiators. This was one of them, right? So this is going to break apart so that each oxygen takes an electron, right? So we get that right there. Let me do it in red. And so now they break apart by having heat to become RO radical twice. Right? So you can just write 2 RO radicals. Well, it turns out that this by itself isn't going to do anything for us, because notice that this product doesn't have anything with the RO. So in other words, I'm not writing alcohol or something here. So remember, propagation is always going to begin when I start to do something to modify my reactant to become its product. So we always show propagation there. So for example, in our example above, I want an H to come into the, notice how this carbon has one H, now it has 2. So I want to add an H and a Br onto the alkene. And so I'm not ready for propagation, because this right here is not going to give us an H or give us a Br. So I'm still in initiation. This is called I2, or just, yeah, I guess I1, I2. And with this one, this is a little unusual. It's not the initiation that you normally would think to see. So normally initiation is always where non-radical becomes radical, but here it's kind of like a propagation, but it's really not a propagation, okay? And as I mentioned to you before, you know propagation is propagation when you're somehow building the product or products that you're trying to make. That's how you know. So if on this side of the arrow, right over here, on the right side of the arrow, if this became one of those products, or in this case just one piece of this product, then you know it's propagation. Anyway, so this is going to collide with an HBr, and that'll hit the H and the Br becomes a radical. So now we have an alcohol, right? I don't need two, by the way. I can just write one, although this would happen twice, right? So we have ROH, and more importantly, we have Br radical. Now we're ready for propagation because this Br is going to collide into the alkene, giving us a connection with the Br. So the next step, P1, is where we have our alkene plus our Br radical. And by the way, P is always a non-radical and a radical. Initiation, up until now, has always been a non-radical becoming a radical. But as you can see, this is initiation, but it's kind of like a propagation, right? It looks like propagation. Just remember that propagation is always where you're building your products. So this is going to collide onto the carbon. And here's the logic. If it hits the carbon on the end, then the carbon is going to become a radical further in. And that makes sense because just like carbocation, radicals are more stable on a higher degree. So radical stability is exactly the same as cation stability, right? And that's what we learned about back in the theory video on radical. Remember how we said the bond dissociation energy? We said it's easier to pull off an H from a higher degree than a lower degree. Well, this is the same idea. We're making a secondary radical, and that's better than if we made a primary. So if the Br went there, then this would be a primary radical formed, and that's not as stable. So that's why, now we see why, the Br actually winds up on the lower degree. It's because it's a radical process, and instead of H coming in first, like up above, H comes in here first, so it goes to the lower degree. In this case, Br is coming in first, so it goes to the lower degree. See that? Okay, hopefully that's clear. Now for P2, we're going to take this, and we're going to collide it with something. Now, it's up to you, but think about this carefully. We don't want to enter into initiation. We want to enter back into P1. Remember how this is the loop? This right here is that whole chain reaction right here. P1, P2, P1, P2, P1, P2. So my goal is to not only put a group here, which we know is an H, right? An H, but we also want to create P1 again. So I'm not going to use the alcohol because that will bring me back into I2 because I'll make this oxygen become a radical. Instead, if I use HBr, right, over here, if I write plus HBr, well then once I put this carbon hits the H and the Br becomes a radical, well now I've made my product, right, plus Br radical. And now I'm ready to take this radical and put it back into P1 and then go through this over and over and over again. So you see how I did that? It's very important that you kind of see that logic. So your P1 ends with something that you drop down into P2, and then P2 ends with what you know you want to drop back up to P1. And that's how I figured out, let me use HBr, because that'll give me a Br radical. All right, so that's it. And now termination, we actually don't even really care about. And so, I mean, you're not going to recreate the peroxide. You actually terminate in some other way. So I'm not going to even bother writing a termination because there's no clean termination that we should concern ourselves with. So in other words, usually termination I like is the opposite of initiation, right? But we're not going to make a peroxide again because it's very unstable. And so that's why we use peroxide. They break apart very easily. And so that's not going to be a good idea to recreate this again. Okay? So it turns out that if you want, just pick any two radicals that you drew out, any two, Br radical with that, or this radical with that. It doesn't matter. So Br, or even the carbons coming together, and they would terminate. So termination, I'll just write more generically, is any two radicals combining. Okay? So it doesn't matter which one. Unlike the other, when I taught you guys this theory, I really went through the energetics and the energy diagram. We're not going to do that now.